Hello, my name is Saransh Verma,
And my name is Ravi Patel.
and this is our cs225 final project, Flyride. So let's talk about our data source and goals for this project. So for this project, we decided to use the Open Flights dataset to use graph algorithms to figure out how to optimize flight routes for maximum customer convenience, comfort, and affordability. So we had four goals for our project: represent our graph as a graph with a specific weight attribute, build a breadth-first search algorithm that runs in OE plus V time, find the shortest path between two airports using Dijkstra's algorithm with a runtime of OV log V plus E log V, and utilize the betweenness centrality algorithm to determine the most significant airport connecting the entire graph with a runtime of OV times E plus E squared times log V. Now, let's talk about our development process. So the first week of our development, we mostly focused on data processing. We downloaded a data set in raw data form and stored in a .dat file in our master repository. And for this project, we focused on two aspects of the data set, the airport and the route. We decided to use a Python script in order to convert raw data into CSV format within the repository. And we cut all in unnecessary naming and sourcing data, leaving just the unique OpenFlight's ID and GPS coordinates for each airport data point. Now, let's talk about the most challenging part of processing our data. So the most challenging part of processing our data was filling in the missing data for efficiently loading our data into a graph structure. For our airport routes dataset, there were two pieces of information given for the airport: the Open Flights Identification Number and the International Air Transport Association, or IATA, number. But for the majority of dataset, either one of these two entries were missing. So we had to have a mapping structure for mapping from IATA code to Open Flights ID number. And since the airport's information dataset provided to Open Flights ID to every airport, but it was not provided for IATA, and that caused a lot of complications.
Now it's the second week of our development process. After we have processed our data, it is time for us to come up with the most important decision: what graph representation to choose. Since we plan to implement Dijkstra's algorithm for determining the shortest path between two airports, which required efficient retrieval of incident edges, and the betweenness centrality, which exclusively relied on Dijkstra's algorithm, we knew adjacency list was the best option for us. Because the way we implemented our graph data structure, finding incident edges was constant time operation. Another factor that helped us in choosing adjacency list is that, like most real world data set, the airport data set is very sparse. So it is inefficient for us to store sparse data set in adjacency matrix, which takes n squared space complexity. By the end of second week, we were well on our path to implement Dijkstra's algorithm. Dijkstra's algorithm is very simple to understand, as it takes a greedy approach for finding the shortest path. We had our first version of the algorithm implemented using an ordinary queue, which was very similar to how we implemented BFS. But we quickly realized that using queue worsens the time complexity to the number of vertices squared. So we changed from using queue to a priority queue, which we designed as a team, especially to allow key updating functionality missing in STL provided priority queue. Making this change brought on an overall time complexity for Dijkstra's algorithm to big O of V plus E times log of V, where V is the number of vertices and E is the number of edges. For the beginning of the third week, and the final week, we plan to dedicate the majority of our time to refactoring the code base, writing test cases, and implementing our last algorithm, the betweenness centrality algorithm. This part of the project was the most challenging for us, as we had minimal mathematical understanding of how betweenness is calculated from a network of nodes. We had to do research to fully understand the algorithm logic. And after having enough understanding, we had our first version of the algorithm out by the midweek, which had a time complexity of big O of n to the fourth. To improve the efficiency, we re-examined the implementation and came to the realization that we can use a map to minimize the number of function calls for Dijkstra's algorithm, which brought our time complexity to n cubed.
So now let's talk about the insights driven from our data set. And one of the things we were able to find from our data set was actually the most connected airport. Now, first, when we examined the first 100 airports in our data set, we found that the most connected airport was the Edmonton International Airport. When we examined the first 250 airports, we found that was the Montreal International Airport. Now, we found that as we were finding the most connected airports using a data set, that it had a correlation with passenger traffic. We did a simple Google search and found that both Edmonton and Montreal International Airports were both some of the busiest airports in Canada. Now, as we expanded our number of airports, we predict that this data is going to become, there's going to be more of a correlation between passenger traffic and the most connected airport.
Although we did not get our algorithms to work fully at scale, we thoroughly tested each algorithm's logic for possible edge cases and reasonably complicated graph structures, which makes our project very much scalable in the future if we refactor our code base.
Now, our final thoughts. Honestly, if we had more time, we would probably examine the larger data set, which could allow us to provide a more accurate result of what the most connected airport would be. In a data set in the first 100 airports and the first 250 airports, you probably noticed that those airports were Canadian. If we maybe examined more airports, we could have got some US airports that could be even more connected than the airports that we already examined.
We would have also utilized our BFS algorithm in an interesting way to find the longest cycle of airports if we had more time. Other than that, I have also planned on having another functionality, which was finding the nearest airport to a set of airport provided for a group of people, which would be an interesting challenge for as a project. But in the end, I would say what I have learned the most from this project is working with the team and leading a team. I've also learned how to utilize algorithm ideas and not actual implementation to build on new ideas and new implementations for solving complex problems. And that was our final cs225 final project. Thank you.
Thank you.